And so an evening to you all, and it's really nice to see all of you, and it's especially nice to see some young people in the crowd, hopefully aspiring astronomers. I'm looking at you. So, right, I haven't plugged my talk in. Good. Right, let's do that. Hopefully, any day now, right? Right, so my talk today is on extrasolar planets and habitability in the age of Kepler. Okay, and so to start with, by extrasolar planets, I mean planets outside our own solar system, planets which are not orbiting the sun, but instead orbiting other stars, right? And as you know, for the longest time in history, we only knew the planets in our own solar system. In recent years, so since 1995, when we found the first extrasolar planet, and it was a huge discovery, I was just finishing my undergraduate at that time. And since then, especially in the last several years, in the last 9 years or so, we have found thousands of extrasolar planets around nearby stars, right? And almost all of that is because of the Kepler Space Telescope, which has revolutionized the field. So my task today is to take you through some of these observations and to tell you some of the things we have learned, exciting things we have learned about exoplanets. And of course, the ultimate ambition in all of this is to search for life, right? Is there life elsewhere? Are other extrasolar planets actually habitable? And if they are habitable, are they perhaps even inhabited? And so I will end my talk by showing you the implications of these observations so far and to tell you how far we can go in the next few years on this. Right, so to start with though, sort of the scope of it, right? So if you go out on a really dark night out in the countryside somewhere and you look up at the night sky, you'll see about 2,000 to 3,000 stars, depending on your eyesight, right? But we know that's obviously only all that your eyes can see. Our sun is embedded in a galaxy, our own galaxy, and it's called the Milky Way galaxy, right? And again, if you are out on a dark night and you look up, you will see the Milky Way galaxy appear like that across the sky in a band, okay? It's not obviously a band. In fact, it's a spiral galaxy. It appears a band because we happen to be in the plane of the galaxy, okay? If you were able to rise above the galaxy and look at it from above, it would appear like that, okay? And so you see that in the center there, you have a lot of star formation going on, and in the center also embedded, you have a supermassive black hole, which I will not talk about. Perhaps we will have another talk on that some other day, right? And then around that, you have these spiral arms, this absolutely lovely image. And the sun is around here somewhere, about a third of the way out from the center, and it's lost among this huge number of stars inside our own galaxy, right? So the first thing to ask is the scale of the galaxy itself, right? So the size of our own galaxy is about 150,000 light years, right? And remember that light year is how far light can travel in a year at a speed of 300,000 kilometers per second. Okay, so 150,000 light years is an enormous distance, right? And inside this large galaxy, you have about 400 billion stars. Okay, and so our sun is really lost inside this enormous number of stars in here, right? So even if a small fraction of the stars in our own galaxy had planets around them, and an even smaller fraction of them turned out to be habitable, it would still be a huge number of planets. Okay, we don't have to confine ourselves to our own galaxy. We can ask how many galaxies are there in the observable universe, right? So this is a picture I've shown some of you before, and I always love showing it, and I feel it's something you should look at every day, but there you go, right? Can you all see that, right? Actually, if someone can turn off the lights over there back for a second, I'd just like you to appreciate this image for a second, right? All right, so just look at that for just a second. Well, we'll leave it like that, right? So, and I just gone mad, right? Okay. So this is a tiny area of the sky about the size of an American dime. So now I'm moving, nothing else. Why is it? Okay, so we'll leave it like that. I think you have a sense of it. This is a size of the sky about this big, right? About an American dime, and it appears. Josh, are you around to do anything about the fact that even my lights don't seem to be working? Right. And the Hubble Space Telescope stared at this for about 11 days and nights. Okay, let's not do anything else. And this is the image it came up with. And the astonishing thing about this image is that every tiny little point of light you see on this is an individual galaxy. Okay? And in this image alone, you have about 10,000 galaxies, each of them on order of about 100 billion stars. Okay? Now, this is only a tiny patch of the sky, right? So if you added up all those little tiny patches of sky over the entirety of the sky, you would reach the astonishing number that the observable universe has 100 billion galaxies in it. Each of them on average with about 100 billion stars in them, which gives you the unimaginable number of about 10 to the power of 22 stars in the galaxy. Right? There's no way you can actually imagine that number. Just to give you a sense, that is hugely larger than all the grains of sand on all the beaches of Earth. Right? So when people say stars like sand on the ocean beaches, in fact, it's far, far more. Right? So the number of stars we have is enormous. So if the universe would like to have extrasolar planets and habitable planets, it has a lot of room to do it. Okay? So we want to know how true it is that stars have a lot of planets around them or don't, and we are in fact alone in the universe, which would be sad, but it would also be an enormously important piece of knowledge. Right? Okay, so now let's sort of reduce again in scale, right? And look at our own solar system, right? So this is a picture of our own solar system. There's the sun, and then you have all the planets over here: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Pluto, as you all know, is no longer considered a planet, right? So it's among all the other rocks in the outer solar system. This image is in scale in the sense that the size of the individual planets are shown to scale. So on the inside, you have these small rocky planets. On the outside, you have these much larger gas giants. It's not shown in scale in terms of the orbital radius out from the sun, because it would be hard to show it on a single image, because as you know, Neptune is something like 30 times as far away from the sun as the Earth is. So in fact, I would need an image going all the way out to the street. Right? Anyway, so the first thing we can ask as we search for extrasolar planets is, A, obviously, are they there? And then secondly, is the architecture of these extrasolar stellar systems the same as we see in our own solar system, right? Do we have these small things on the inside and large things on the outside and so forth? Okay. The other thing we can ask is, in our own solar system, we have a habitable zone, right? And the Earth is in the habitable zone, obviously, because it's inhabited, okay? The definition of a habitable zone, sort of, is the region, the orbital distances, where if you have an Earth-like planet on its surface, you can find liquid water. Right? So if you have a planet which is about the same size as the Earth and so forth, and has an atmospheric composition like the Earth, then it is a distance where the star provides enough energy to the surface to have it hot enough in order for H2O to be in liquid form. Right? Why do we concentrate on liquid water when we are talking about habitability? It's because we have a statistic of life of only one, right? So all that we know about life is on the Earth. So we don't know really the thing we're looking for if we're going to go out and hunt for life. But we do know that all life on Earth, without exception as far as I know so far, always requires liquid water. Okay? So we're going to choose the only thing which seems to be common to all life on Earth and say that at least it should be something that we look for. And it's because H2O has some exceptional sort of characteristics which allows life to operate at least on Earth. Right? So we can ask, in other planetary systems, are there planets inside the habitable zone? And can they be habitable? Why is that important? Because, as you see, so the habitable zone, even in our own solar system, includes not just the Earth, but it also includes Venus and Mars. Right? Those two, on the other hand, are not habitable. Mars is too small, it really has no atmosphere. Venus, on the other hand, is almost exactly the same as the Earth, except its atmosphere is completely different because it had another evolution in its atmosphere unlike the Earth's. Right? So just because you're in the habitable zone around a star does not mean that you will end up being habitable. So when you find planets in the habitable zone, the second question you have to ask is, do they have a combination of properties, not necessarily like the Earth, but do they have some combination of properties that allows life on them, right? So that's sort of the series of questions we would like to ask, okay? Right, so having set the stage with that, let's now ask, how do we actually find these things, right? So we have essentially two techniques, and the first one is not the technique used by the Kepler Space Telescope, but I'd like to show you that one first, because historically it was the first one that was used, and that's known as the technique of radial velocities or Doppler shifts, right? And the idea behind that is straightforward. If you have a star with an orbiting planet around it, the planet is orbiting the star because of the gravitational attraction of the star on the planet. Okay? However, by the same token, the planet also exerts a gravitational force on the central star. It's a lot smaller because the planet is a lot smaller than the star. But it does have an influence, and the effect of that influence is the star also describes a small orbit around its own central mass. Okay? So it just sort of jiggles back and forth in place, as it were, right? And if you look at the spectrum of that star, you know, if some of you remember your high school physics, if you have a source of light that is receding, then its spectrum, it will appear to be redshifted, and if it's approaching you, its spectrum will appear to be slightly blue-shifted, right? And so if you observe the spectrum of the star, you can see the spectral lines in it being slightly red-shifted and blue-shifted over time as the star jiggles back and forth in place, right? And if you can detect that, you can hence know the velocity of the star and therefore the size of the planet that is having that influence and also the orbital period of the star around the sun, right? Drawback of this method is that it does not give you the actual mass of the planet. It gives you sort of a lower limit on the mass. Again, I don't have time to go into the reasons for that, but that is a small drawback of the system. At any rate, it was the first thing that we were capable of doing, right? And this is the first planet that was found, 51 Pegasus b is the name it rejoices in, right? And it turns out it's a hot Jupiter around a sun-like star, and I'll explain that in a second. This curve here shows the velocity of the star that this planet orbits as it jiggles back and forth. And as you can see, the velocities are rather large. It's about 50 meters per second. Okay? And so it's a rather large planet in order to have that influence. In particular, this technique is sensitive to large planets because they have a larger gravitational influence, and also to large planets very close to their star because that also increases their gravitational influence. So it's not surprising that the first planet that we found in this method is a hot Jupiter. In other words, it's a planet about the size of Jupiter. It's a gas giant, but it's very, very close to its central star. It's orbiting with a period of only 4.2 days, right? So if you can imagine Jupiter in our own solar system not being way out there at 5 times the distance of Earth from the sun, but instead so close to the sun that in fact the surfaces are almost touching and whirling around the sun in an orbital period of 4.2 days, that's what this system is, right? We didn't know of any such planets before that, obviously, because we don't have them in our own solar system, and therefore it was completely unexpected. But you know how theorists are. As soon as you show them something, they have a theory for it. Okay, so that's not the slide I want to concentrate on. So as soon as we found this, they came up with all kinds of theories why it was always to be expected. Right? And so this is the distribution of planets that theorists said after this observation you should expect. You have small things close in and then larger things further out, and all of this, of course, is coming out of our expectation of our own solar system because that's how things are. An astronomical unit, by the way, is how far the Earth is from the sun. Okay? So the Earth sits at about an Earth mass, at exactly an Earth mass, at exactly an astronomical unit, and then you have small things inwards and larger things outwards, just like in a solar system. But theorists came up with this idea that large things sitting out here, something like Jupiter, occasionally can also migrate inwards really close to the star and end up really close to the star, just like the hot Jupiter we have found, right? So this is the theoretical expectation, say, around 2007, okay? And look at this large hole here. So you don't really expect Earth or something a few times the size of Earth very close to the central star is the expectation. Right, so I'm going to leave you with that picture, and I shall return to it later. Okay. Now, the second technique that we have is called transits. Again, that's the technique that is used by Kepler. And again, the idea is quite simple. Okay. You have a star, and you have a planet orbiting it. Now, if you are looking at it, if the geometry is right, so that the way you look at the system is edge-on, so that the planet occasionally passes in front of the star, then you have an eclipse, a small eclipse of the star, right? So if the planet is behind the star, then you just see the starlight. As it comes out, you just see starlight. And as it passes in front, you see a reduction in the starlight that you see, okay? So if you can see that little reduction in starlight, then you can say something about the planet. And some of you have also seen this in our own solar system. So the inner planets, Mercury and Venus, transit in front of the sun, okay? And we can see that with the naked eye. How many of you have seen transits of the inner planets? Okay, so some of you have seen this, right? And so this is the transit of Venus across the sun, June 5th to 12th in 2012, right? Anyway, so you can see this. So if you see how often this happens, you know the orbital period of the planet. And if you look at how much the starlight is reduced, you have an idea of the size of the planet. Obviously, a small planet incurs a small reduction in the light, and a larger one incurs a larger one. And a smaller star is eclipsed more than a larger star. Okay, so if you have that information, you can say something about it. Notice that this technique, on the other hand, its drawback is that it is limited to systems that you are just seeing edge on. Okay? And so if you see something in this technique, there are a large number of planets you're also not seeing, not because the planet is not there, but just because the geometry is not right for you to see it. So there are statistical corrections you have to make to the observations. Okay? Now, so something about Kepler itself. So this is the technique I said, as I said, Kepler used. So this is the Kepler telescope. It's not orbiting the Earth. It is, in fact, trailing the Earth and orbiting the Sun itself. Okay, so that's the orbit of Kepler around the Sun, and that's because that is a particularly stable orbit. Okay, it spent 9.6 years in space. Okay, so it started around 2009 and ended sometime, I think, in July or something like that in 2018. And its sort of fundamental goal was to stare at a single patch of sky somewhere in the region of the constellations of Cygnus and Lyra, okay? And in its field of view are 150,000 stars, right? And it stared at them constantly to see the occasional small dip in starlight as you had an eclipse in front of the star. In addition to that, because it lasted a lot longer than we expected to, it ended up actually observing a larger part of the sky. So by the end of its lifetime, it had observed about 530,000 odd stars. And it has discovered 2,662 confirmed planets. There are still another 2,500 odd planets which it has detected, but they need to be confirmed through other techniques, because you have other things that can give you the same kinds of effects. Here's an interesting factoid. The amount of fuel it used is exactly 3 gallons of fuel. That's all the amount of fuel it used. Obviously not in the launch, okay, but in its life, okay? So 3 gallons of fuel, only about 670 gigabytes of data. It's not a lot of data, just to see a transit. Okay? But it is enormously sensitive. So these are some of the detections, okay? Sadly, with the lights sort of on, you can't see these too well. The point is, these are sort of the light curves that you find, right? I don't know the reason it hasn't come out too well in this slide. And right, let's leave that off. Turn this down. Okay, and it's found loads and loads of planets, okay? And so this, for example, is a system of 6 closely packed small stars, small planets around a sun-like star. This is another example of about 7 Earth-sized planets around a star called a red dwarf, and I will return to red dwarfs in a moment, okay? So, let's not touch that anymore. Okay, now, so these are some examples of planets Kepler has found. These are the statistics, okay? So I don't know if you can see the numbers at the back. I'll read them out to you. So in the first plot, this is along the x-axis. You have the size of the planets. So this is an Earth radius. This is 2 Earth radii, 4 Earth radii, and so forth. And this is a fraction of sun-like stars with planets, okay, of these sizes inside about a 100-day period, okay? And if you add up these numbers, so this is about 12%, 14%, 18%, etc., you find that about 50% of sun-like stars have planets around them. Now, there's an additional, on top of each of these is sort of a red bit here. So as I said, you see a number of planets, and then you have to have a statistical correction to them to take into account the fact that all systems are sort of essentially randomly oriented in the sky, and you're only seeing the edge on things. So you have to improve the statistics to take those into account, and all of that has been done. So around 50% of sun-like stars appear to have these planets inside about a 100-day period around sun-like stars. Around red dwarf stars, so I should explain red dwarfs. Some of you are old enough to remember the TV series Red Dwarfs, right? Now, so these are small red stars, okay, and they're dim and they're red because they are in fact cool stars. But they're important, extremely important, because it turns out they make up about 80% of all the stars in the galaxy, okay? So sun-like stars are not the norm, okay? Sun-like stars make up only about 15% of all the stars. 80% is these red dwarfs, right? So anything we know about red dwarfs is really important, okay? And this shows the same kind of thing in a different way. This is, again, the planetary radius. This is the cumulative planets per star. So on average, if you looked at any red dwarf, it has, so about a few percent of them have planets of about an Earth radius inside some orbital distance of about 10 days or so. And then as you go outward, the idea is that by the time you reach about 3.5 or 4 Earth radius, okay, this cumulative sum adds up to about 1, okay? So pretty much every red dwarf has at least a planet around it of a few Earth radii, again inside a 100-day period or so. Okay? So the first thing we learn is that if you do all of this, it turns out, nearly all stars have planets, and many of them have multiple planets around them. If you go up and look in the night sky, most of the stars you see have planets around them. And that adds up to hundreds of billions of stars in the galaxy. And in fact, we now know that there are more planets than stars in our galaxy. Okay, so that's an amazing thing to know, right? And this is something we have learned just in the last couple of years after we've actually finished all this sophisticated statistics and so forth. The other thing which I should point out, no, let's not do that yet, is that, these are Earth radius, or a few Earth radii in size. But as I said, they're all inside about a 100-day period. Okay? Keep in mind that Mercury in our own solar system has an 80-day period. Okay? So a large number of these things, almost all of them, are in these systems in which all these planets are packed inside orbits smaller than Mercury's. Right? Again, very, very close to the central star. Okay? So to see that more interestingly, I think, so this is a collection of all, and you'll see some more as the animation runs through. This is a collection of all the systems that Kepler has found in which there is more than a single planet in the system. Okay? And the size of these are scaled to the size of the Earth. The solar system is shown here. Earth is here, so that's the size of the Earth. The colors are essentially the surface temperatures of these things. So blue is about the same surface temperature as the Earth, and the size is scaled up from the Earth. And these are their orbits, and it'll start to run. So the first thing to notice is that so many of these orbits are much, much smaller than the orbit of the Earth. And up here is a time, and these things will start turning around in time, right? So you'll see how fast they circle their stars. And I think there's audio on there, so I might have to turn it down a bit. Let's see. It shows, I think, the diversity of all these planetary systems. We now know planets around binary stars. We know planets around essentially 4 stars in a system. All kinds of things that theorists all say are completely impossible. Okay? And then these are Earth to super-Earth size things in very, very small orbits. Right? So let's go back to the earlier theoretical prediction. Right? So this was sort of the architecture we had expected. If I superimpose on that what Kepler has found, so all of these will be the colored dots. There you go. This has got to be pretty much the worst theoretical prediction in astronomy. Okay? And they all occupy this hole there, right? This line here shows under that, our statistics are not complete. The instruments are not yet sensitive enough to find really small things really far away. But it's okay. All of these things may also be there, but the point is these things which are not supposed to be there at all are there, right? So this is also lucky, because Kepler, we sent it up hoping to find all of these things and maybe some things down here, but instead it found this enormous sort of population in here, okay? So all of these, so in fact, let's examine that population in a little more detail. You have a first population of about Earth to super-Earth size things, about an Earth mass to about a few Earth masses. So these are the Earths to super-Earths. And then you have these things called Mini-Neptunes, which are about 10 to 20 Earth masses. Okay? And they all occupy orbits that are about 1/10 of an astronomical unit or so, right? So well inside Earth's orbit, in orbits usually about that of Mercury's or even smaller. So that's the second result that we have. At least 50% of all stars, okay, at least 50%, half of all stars, if not far more, have Earths or super-Earths or Mini-Neptune-sized planets very, very close to the central star, and this is not found in the solar system. Okay? Earlier on, we thought it is, in fact, just about 50%, so, half the stars have them, half the stars don't, the solar system just happens to be in the half that does not. Now the situation is getting slightly more tricky because we're climbing up towards about 70%, right? So the solar system does appear to be slightly odd, okay? And we don't know why. Okay, so that's the second result. The third result that we'll come to is that let's examine this same plot again. Now, let's in fact concentrate on these Earths and super-Earths and even smaller planets that Kepler has been finding. Now, these planets, when they are so close to the central star, if the central star happens to be a sun-like star, then they're obviously far, far too hot to support life. They're certainly not in the habitable zone. The habitable zone around the sun is not inside the orbit of Mercury, right? Much further out. But most of these things are around red dwarfs, right, which I said are these small, cool, faint things, right, which are much, much cooler. And so their habitable zones are much closer to the central star. So while we had sent Kepler up to try and find maybe a few habitable planets around sun-like stars, it's found, as we'll see, a triumph of planets in the habitable zone around red dwarfs. So let me just show you the habitable zone around red dwarfs. So this is a sun-like star. So this blue thing over here is the habitable zone, according to theoretical calculations. Around sun-like stars, it's out around the orbit of the Earth. Around a red dwarf, on the other hand, the habitable zone is in fact exactly around 1/10 of an AU, which is where all these things are. Okay? So now we know, and so we have some statistics. Again, I don't know the reason this is not showing these plots too well. Around sun-like stars, we have found a few, so numbers are at least about 20% of sun-like stars have these planets in the habitable zone, but this is sort of the histogram to look at. This is the number of planets per star, and this is insolation, so how much radiation sort of the planet is receiving, which is a handy way of saying, is it receiving sufficient radiation to be hot enough on its surface to have liquid water, right? And this is sort of the habitable zone shown by these dashed lines here, right? And if you add up all these numbers, it turns out that the most conservative estimate is around 25% of these red dwarfs have planets in small planets, okay? So these are small rocky planets inside the habitable zone, and on the upper limit side is about 80% of them do, okay? So that's the third conclusion we have. A significant fraction of stars have Earth or super-Earths in the habitable zone, at least about 20% of sun-like stars, and anywhere from 20 to 80% of red dwarfs, okay? And that implies already, even if you take the conservative estimates, that at least tens of billions of potentially habitable rocky planets are in our galaxy alone around red dwarfs, because red dwarfs make up, as I said, about 80% of all stars in galaxy. The number of stars in the galaxy is around 400 billion. 80% of that is around 300 billion. 20% of 300 billion is a lot of planets. Okay? Right? So, earlier on, about 10 years ago, if you had asked astronomers what these numbers or these percentages should be, we would timidly say, well, we hope it's around 1%, 0.5%, right? So not in our wildest dreams did we think that would be the answer, okay? Now, we can find things also about the atmospheres of these planets now, so I'll have to rush a little bit, but hopefully finish in time. Right, so, okay, so note that if you have a system like this where the planet is passing in front of the star, okay, then you can also say something about its atmosphere. The reason is, as it does, the starlight passes through the atmosphere of the planet. Right? If the planet is in front of the star, starlight has to pass through the atmosphere. And so if you see that starlight, it has the chemical signatures of the planet's atmosphere embedded on it. Right? You can also do something else. You can say, okay, I'm going to obtain a spectrum of the system when I see the planet and the star, and a second spectrum when the planet is behind the star. If I subtract those two things, I have an emission spectrum of the planet alone, right? So those are the two ways that you can actually obtain these spectra, right? I'm just saying all of this without actually giving you an idea of the technological advance this requires, okay? So let me just actually say that. The first detection technique I had shown you of how the star actually jiggles around, we are sensitive now to stars jiggling at a speed of 1 centimeter per second, or a few centimeters per second, okay? That is enormously slower than the speed at which you walk, okay? When Kepler sees these small changes in the starlight, okay, as the planet is eclipsed, it has to be sensitive to light at the level of being able to detect a candle on the moon, okay? And these atmospheric calculations are then the equivalent of not just being able to observe the candle on the moon, but being actually able to tell you the composition of the flame. Okay. Right, so I'm not going to take you through all of this. Suffice it to say that we have learned a lot about these atmospheres, and we can do amazing things, right? So, for example, these are all the sort of observations, and I apologize for the quality of some of these spectra. Or some of these plots. I think it's something to do with incompatibility of my AV system on the Mac. But at any rate, we can say things like, this is observation of a hot Jupiter, and we can say things like, we think if you look at it, it will appear blue. because we can see Rayleigh scattering in this atmosphere, which is the same thing that also makes the Earth sky blue. We can do things like we can look at the surface of the planet as it rotates and tell you the temperatures on the surface of the planet, or at least in the atmosphere, as a function of its latitude, okay, etc., etc. And these are some other observations. I will not go into it. But what we have really learned from these observations, okay, and this is the key part of it, is that most of these close-in Earths and super-Earths around sun-like stars as well as around red dwarfs, when they're born with thick hydrogen-helium atmospheres, which make up about 1% of the planetary mass. Okay? That is entirely unexpected, again, because we don't see things like that in our own solar system. And why is that important? It's because hydrogen, and we don't think of hydrogen as a greenhouse gas because it's not there in the Earth's atmosphere, but in fact it's a very strong greenhouse gas. Okay? So if you have 1% of the planetary mass in hydrogen and helium, then the surface temperatures of the planet are far too high to be able to sustain liquid water. Okay? In comparison, for example, the atmosphere of the Earth is only around 10 to the minus 4% of the Earth's mass. Okay, so about 10,000th of a percent of the planetary mass, as opposed to being 1%. Okay, so these are really thick things. So if these planets continue to harbor such atmospheres as they evolve, then they will not be habitable. Okay, so nature seems to have dealt a sort of a dud hand. On the one hand, it's given us tens of billions of these potentially habitable planets inside the habitable zone, but then, it turns around and says, well, initially they have all these thick hydrogen-helium envelopes, so, close but no cigar, right? However, all is not lost. Okay, so we know that stars are active. Okay, our own sun is active. It has flares. It has ejections and so on and so forth. And these flares and ejections are these, extremely energetic charged particles. And all of these things hit the atmospheres of the planets around them. So this is a little movie of the actual sun, where the actual sun is sort of blocked out. So you can see the stuff happening in the atmosphere of the sun, the corona of the sun, obtained by this SOHO-LASCO C2 instrument in space. And so this is how, whoops, hello, we'll make it run, right. And you'll see, these ejections and flares happen, and they're quite spectacular, right. It runs for about 30 seconds, right. These huge flares coming up, right, enormous amount of charged particles being thrown out, etc. And all of these things impinge on the atmospheres of the planets, okay. And on it goes, right. But that's not all, right? Because the sun is active, apart from all these flares and stuff, it also shoves out a large amount of X-ray photons, right? So the sun is luminous in X-rays and in ultraviolet photons, right? And so this is an image obtained by the New Star Space Telescope again, which observes in hard X-rays, high-energy X-rays, and again you can see the sun shining in X-rays, right? And all of these X-ray and high-energy ultraviolet photons can also hit the atmospheres of the planets. The effect of these high-energy photons and high-energy particles is that they scour away the atmospheres. They can ablate the atmospheres or evaporate these atmospheres, okay? So the important thing here is then that we know that red dwarfs, which are also known as M dwarfs, I'm sorry if I've said M dwarfs from time to time, so these red dwarfs are not just active, they're about 1,000 times more active than the sun is. Okay? So if you have these thick hydrogen-helium envelopes around these stars, around these planets, then there is a possibility that they can be evaporated away by this high-energy radiation and these particles, and therefore end up with hardly any atmospheres, and therefore in the end be, in fact, habitable in losing these thick atmospheres. Okay? And so this is sort of a cartoon or a simulation. It's not a cartoon. It's a simulation of how this evaporation happens. So here's the star. Here are the XUV photons, and in the center you will see a planet. There's a planet, and it's being evaporated away. All of this stuff is escaping. Its atmosphere is escaping out into space, and it's being evaporated away. Okay, so that's the picture that we expect, right? So this is is this actually seen? And the answer is in fact stop. Right? Can we carry on? Yes. So these are some theoretical calculations that were done early in 2017. In fact, the paper, it was submitted, I believe, at the end of 2016. I can't remember the exact dates anymore. By, in fact, James Owen, who is at Imperial, also in the Astro group, and his collaborator, Yinchin Wu. And they showed that around sun-like stars, you have such evaporation. And what you expect because of this evaporation is two populations of these planets. Okay? You have these close-in rocky planets that start out with these thick hydrogen-helium envelopes. Because of the evaporation, you would end up with two populations of planets. Planets which are too large to essentially lose any of that, so they retain atmospheres of about 1% or so, and then planets which essentially lose all their atmospheres and end up in a second population here. Okay? So it's not a continuum of atmospheres that you would expect because of, again, physics I don't have time to go into. You either should have a population which has about 1% atmosphere in hydrogen helium and a second population which has lost everything. Okay? And so this was the prediction, and these were the observations that came out just a few days later. Okay? So here you see, so observations, they don't ever look as good as theory, but you distinctly see two populations here, right? So in the colors of it here are sort of the added up statistics of all these observations, and you see a distinct over density of planets here and another population at a lower bound here, right? So unlike the earlier prediction I showed you, which was terribly, terribly off, this one actually seems to be on the money. Okay? So this is the kind of thing that happens around solar-type stars, observationally confirmed now. Evaporation happens. Okay? And so, but these calculations and these observations are for sun-like stars. We really don't have as much data or as much high signal to noise data for the planets around these M dwarfs of their atmospheres to have an idea observationally if this is happening, but that has not stopped theorists like us. So we have carried on and applied the same theory to the planets that we know exist in these habitable zone around red dwarfs. Okay? So exactly the same science that has been confirmed around solar-type stars to make a prediction of what we expect to find around red dwarfs. Okay? And the prediction is, again, since you can't see the numbers, I'm not going to say anything, but all it means, all these lines show is that you start out with a % atmosphere and then you evaporate away, and this side is for an Earth mass planet, this side is for a planet which has a Venus mass. Okay? And as you can see from these lines here, okay, you essentially lose just a little bit. So an Earth mass planet around a red dwarf in the habitable zone hardly loses any atmosphere, and our prediction is it will remain uninhabitable. But if you're just a little bit smaller, Venus is 0.8 Earth masses. Okay? If you're just a bit smaller, you will evaporate away all its hydrogen-helium atmosphere. Okay? So in fact, in this large population of planets we are now finding around M dwarfs, you have Earths and super-Earths, which we think will not be habitable, but you also have an increasing number of these smaller planets that we are finding, and we expect them to actually lose their hydrogen-helium envelopes. So if you lose all your atmosphere, of course, then you are, again, not going to be habitable, right? So you need some amount of atmosphere. So how did it work on the Earth, right? The way it worked on the Earth is that the Earth initially also had some hydrogen-helium. It got evaporated away, okay? But in the end, the Earth's atmosphere that we see today is not the atmosphere that it was, in fact, born with, but atmosphere that was outgassed from the interior. There's also we also expected that a large amount of the Earth's atmosphere came from outside the Earth through impacts from comets and asteroids. That expectation seems to be less likely these days. Okay, again, for science which I don't have time to go into, but I can certainly answer that if you ask me about it later on. So the idea is that through this evaporation, these planets will lose the hydrogen-helium envelopes, and then outgassing and so forth, as has happened on the Earth, is going to repopulate the planet with a small, thin atmosphere, a secondary atmosphere, just like on the Earth, and you would expect to be habitable. And the reason we are optimistic about it is because when you have these complicated atmospheres of oxygen and CO2 and so forth, it's not so easy to evaporate them away, right? Because these are larger molecules and heavier molecules, okay? And so I think the idea then is that, or the conclusion is that red dwarfs, we think, can evaporate away their initial thick hydrogen-helium atmospheres if you are a planet that is sufficiently small, say something about the size of Venus or smaller, and then secondary atmospheres can then make the planets habitable. The calculations are ongoing. We are doing those now, so stay tuned. We should have something published in the next year or so. And the observations of this are starting now as well. So we should have observational evidence of if our predictions are right or not. And on that note, I've come to the last 2 slides, I think. This is a slide of the instruments that have helped us so far and the instruments that we expect in the near future. Okay? So the instruments I have spoken of so far are, of course, the Kepler Space Telescope itself, and then when you find planets with it, the additional observations of the atmospheres and so forth happen on the HST, the Hubble Space Telescope, and also the Spitzer Space Telescope, which had initially hired me as a postdoctoral fellow in the early 2000s. Unlike the Hubble, the Spitzer has now died, okay, so that's no longer there. We also have the largest telescopes on the Earth itself, which are the Keck telescopes. Each of these is about 10 meters across. Then you have the VLT, which is the very large telescopes, okay, so astronomers have little imagination, as you'll see in a second, right, which are 4 telescopes about 8 meters across. So all of these have observed these planets with, either directly or in follow-up observations, right. Replacing HST and Spitzer is JWST, which is a James Webb Space Telescope, which was supposed to be launched in 2020, has now been shifted, I believe, to 2021. We'll see. Anyway, but that it's a huge telescope, right? It's 6.5 meters across as opposed to 2.5 meters on the Hubble, right? And that is really going to, again, revolutionize our understanding of the atmospheres of these planets, right? Because it has extremely powerful spectrographs. It'll observe all the way into the infrared, okay? And we will learn a tremendous amount about these planetary atmospheres. Then you have the TESS telescope, which is an acronym whose full form I always forget, but you will remind me. The Transit Earth Survey Satellite. Have I got that? Transit Exoplanet Survey Satellite, I think, right? Right. And that has already been launched earlier, I think it was late last year, and has successfully started taking observations, had successfully already observed an exoplanet that we knew existed as a test observation. Compared to about the 3,000 odd planets that we have already confirmed or have in candidate status now, TESS in its 2 years of observation is supposed to find about 20,000 planets. It targets about 1,000, or is it 10,000? I forget. 1,000, I think, of the closest stars to the Earth, okay, including the closest red dwarfs, okay? So most of the stars close to us are, in fact, red dwarfs because they are about 80% of all stars. Then you have the Plato telescope, which launches, I can't remember, 2026 or something. So all of these are in space, all observing planet transits and atmospheres. Then you have the GMT, which is the Giant Magellan Telescope, already under construction in Chile. You have the TMT, which has also just been approved. That's the 30-meter telescope. Wait for it. And then you have the ELT. Any guesses? The extremely large telescope, right? And it is extremely large. Okay, it is 40 meters across. Okay, so here for comparison is one of these VLTs, 8 meters across, standing next to the ELT in this rendition. It feels tiny. That has already been approved. Construction on it has started already. So it should be starting. It should start operations, I believe, somewhere in the late 2020s and be fully operational in the early 2030s. There are even more, I think, grandiose plans. There is, as an example, around the 2050s, we hope to start on something called the OWL. Any takers? Overwhelmingly large telescope, which we dream is going to be 100 meters across. Okay, an optical telescope 100 meters across. Right? Anyway, but so far all of these are approved. And why is this so exciting, really? Because, I want to show you a last slide. And thankfully, this has shown up all right. And I want you to concentrate on this. As I said, a test which is already launched is going to be looking at about 1,000 of the closest stars. A large number of them are red dwarfs. And it's going to be looking for exoplanets in the habitable zone. Now, the first technique I showed you, which finds things because of the shift in the star, is now, as I said, enormously sensitive and can see things at a few centimeters per second. And just last year, is it last year? No, in 2016, I think late 2016, it found a planet about the size of the Earth in the habitable zone around a red dwarf. And that red dwarf happens to be the closest star to the Earth, right? Proxima Centauri. Okay, it's right here. There's a red dwarf. This is the data. Okay, it looks a little ratty. But if you average over it, there's an Earth mass signal. Okay, so the fact that around the closest star to the Earth, which happens to be a red dwarf, you find a planet of about the size of the Earth in the habitable zone, either we are tremendously lucky, but the statistics suggest otherwise. We have found it in the first shot because they're everywhere. Okay, and Tess is going to show us. So on that note, I shall end and take questions and turn off the volumes. Hello? Yes? I think I might need to turn up the volume, so turn that off, because I think Panopto stops if I turn down the volume. Okay, right. Happy to take questions. Yes?
Were there any exoplanets detected orbiting around the neutron star?
Right. So, in fact, the first exoplanets ever discovered were around a neutron star, right? And this was ages ago. This was back in the 60s, I believe. Right? It was not discovered through any of these techniques. It was discovered from the gravitational influence on the neutron star itself and its spin. People sort of, they said, interesting, but since it's hard to do those observations, and also because these are obviously the husks of original planets, right? Because a neutron star at some point had exploded in a supernova, etc., etc. So these planets were unlikely to be habitable or to say anything about how planetary systems usually are. So even though we had found them, we sort of didn't really pay a lot of attention to them. Now we are starting to, because we are interested in how all of these planets we are finding are going to look when these stars, all these stars, start becoming supergiants and novae and supernovae, etc. So yes.
If the red dwarfs are very much more active than the Sun, and the habitable zone planets are actually very close in, surely the conditions will be rather unstable on those planets, particularly if they're open magnetic field.
Right. So there's that's exactly the reason, I think, to start with, that we are actually undertaking the quantitative calculations at the moment. But there are two answers to that. The first one is that, you know, the magnetic field part, which you raise, is really important for planets in the solar system, okay? And that's because most of the energetic output of the active sun is in the form of charged particles, okay? And so if you do not have a magnetic field, then the idea is that you cannot, in fact, keep these charged particles out, and it'll scour away the atmosphere and so forth, as possibly as has happened on Mars, for example. But note that the magnetic field has no effect on photons, on X-rays and ultraviolet photons. Okay, so when we talk about M-dwarf activity, they are in fact highly active in X-rays and ultraviolet. Okay, so the magnetic field really becomes not that important, and they continue to be active much, much later into their lives. Okay, but it is on the other hand, these X-rays and ultraviolet photons also, at some point, the activity stops. Okay, so M-dwarfs start to become less active after about a few 100 million years. Okay, so depending on when the outgassing from the interior happens and which things are outgassed, right, and how active that particular M-dwarf is, the answers are likely to change. Okay, so the Earth, for example, was formed not very early in the solar system, but seems to have been formed at an age of around 30 billion years or so. And the outgassing, we expect, continued up to a few 100 million years. So there's enough time there. So it is likely that planets around M-dwarfs are going to have a later start in life, as it were, right? But we are checking. Yes?
With these planets being very close to the star, are they likely to be tidally locked?
Yes.
Is that going to affect the habitability of them?
Right. So again, I think theorists arrived there first and slightly wrong-footed. We predicted that. I mean, I say that as a theorist. I don't mean that I personally said so. But I have to say these things because it's being recorded, right? And I just want to make sure that people don't catch me out. But anyway, so they are in fact tidally locked. That prediction is true because it's simple gravitational mechanics. But in terms of affecting the habitability, it turns out the situation is much more complicated. What we had expected is that if you're tidally locked, so I should explain tidally locked, okay? So tidally locked is if you are, tidally locked is the situation between the Earth and the Moon, okay? You always see the same face of the Moon, okay? And that's because the gravitational attraction of the Earth on the Moon and the other way around, the tides, essentially, that they raise on each other, means that the Moon always keeps the same face to the Earth. It doesn't mean that it doesn't rotate. It means that its rotation period on its axis is the same as its orbital period around the planet. Okay, so it just goes around like that. Okay. Now we had expected, therefore, if the same face of the planet is always facing the star, then you're going to have, you know, this side be really hot, the other side be really cold, and so even if you're in the habitable zone, in fact, you're going to be either too hot or too cold for life. Turns out hydrodynamics comes to the rescue, so if you have a really hot part and a really cold part, you get these winds, right, that circulate to equilibrate the temperatures, okay? Now, these are really fast winds, right? So some of the winds that we have seen now in actual observations are hundreds of kilometers per hour, right? So the objection to life might not be too hot or too cold, but in fact too windy, right? We'll see. Yes.
We'll take one more question, and then I think in the interest of time, we will leave the main lecture there. But if you do have extra questions after this gentleman, please do come down the front and ask Subu yourself. He'll be very happy to
There's
take
enough room there. Yes.
Oh, thank you for the lecture. It was really fun. I was interested in what your thoughts were on the chemical signatures for life, and kind of whether the next crop of instruments that we mentioned are going to be sensitive enough to find anything about that.
Right. So I think it's an excellent question, and a speaker always says that in order to buy time. It is an excellent question. So it's got two parts, right? Which signatures signify life? Okay, and the answer is we know, but it's confusing, right? So in the Earth, as an example, we have oxygen in the atmosphere. The general answer is, if you see any chemical element which is out of chemical equilibrium in the absence of life. So an excellent example is oxygen in the Earth's atmosphere, right? So oxygen is extremely reactive. It oxidizes things. If you did not have life, always resupplying the oxygen, it would simply interact with all the other elements around and turn to rust, as in fact it has on Mars, right? That's why Mars appears red, right? All the oxygen is in rust, right, on the surface. So you have to have something that is resupplying the oxygen, right? But on the other hand, you know, again, also things like CH4 and O3 as in ozone and all that, right? But you also have geological processes that might also lead to the same thing. As an example, if you have H2O in the atmosphere, right? If you have steam in the atmosphere, clouds in the atmosphere, if you have a lot of ultraviolet radiation, then that dissociates the H2O into H and O, okay? Then the H evaporates away and the O remains, okay? Because it's too heavy to get, right? So you have all of these other things that come in as well. Then the other thing is that, you know, even if we do have signatures and we are able to rule out any other sort of non-biological ways in which they can arise, are we in fact sensitive enough to see them? Okay? JWST is going to be sensitive to see some things like H2O or CH4, I believe, right? But in order to really be able to see the signatures of life, I think we'll have to wait for things like the ELT, right, around the early 2030s. And there are other instruments in the planning stage, depending on, I think, the outcomes of these telescopes over here. So in the next 2 to 5 years, I think if we have enough evidence that we should go out there hunting, then we will. Okay? And in fact, because we can only look around the closest stars, okay, because, you know, to have enough signal to noise. So if we find that they're absolutely chockers with habitable planets and habitable zones, then we'll look. So.
And I think we'll leave it there. So if you do have any more questions for Suga, please do come down the front at the end of the lecture. Please ask him. If you have any good questions that you think are on the way home, and you think, I should have asked that, tweet us at Imperial